Hello. Thanks for introduction. So, sorry. Hi, everyone. My name is Yue. I'm from UC Riverside. Today, I'm talking about our work, which is about our past TCP attack by exploiting a global rate limit in recent Linux kernel as a side channel. This work is a collaboration with Army Research Lab. Well, TCP is such an old protocol. You may wonder why the heck we are studying it. Well, since it's a fundamental lower layer protocol, its security affects the upper layer protocol, such as TLS, as we will show this in this talk. In our work, we discover a subtle TCP side channel vulnerability in Linux kernel 3.6 and beyond. Given any two arbitrary hosts on the internet, blind attacker can exploit this vulnerability to infer the existence of communication, the sequence number in use and ACK number in use. Well, this can in turn be used for TCP connection termination attack and malicious data injection attack. This side channel vulnerability affects all Linux kernels since late 2012. In my presentation, I will first talk about the threat model. Then I will give the background information. After that, I'm going to talk about the vulnerability, our attack, and evaluation. And finally, I will give some possible defense and conclude our work. Let's look at the threat model first. Our threat model is a very common setting. Given any arbitrary pair of client and server, a blind all-pass attacker is trying to interfere their connection. All-pass attacker means hacker can be anywhere with no man in the middle needed. Since our attack is pure all-pass, without running any malicious code on client side, attacker is unable to eavesdrop any packets and states between client and server. Any machine might act as the attacker in this model as long as it's allowed to send spoofed packet in network with client or server's IP address. Now let's look at the background. Well, security was not the primary concern in the design of TCP, so there have been many security patches over years. With our threat model, the most common attack are the traditional blind in-window attacks. An all-pass attacker can send spoofed TCP packets by brute forcing all possible sequence numbers to achieve connection termination or data injection attacks. To succeed in such an attack, it's necessary to know 4 tuples: source IP, destination IP, source port, and destination port, or a TCP connection. Besides, the guest sequence number should fall in the receive window. To defend against such attacks, RFC 5961 proposed 3 modifications with the receiving schemes. Ironically, we discovered those 3 modifications create an even more serious vulnerability. Linux introduced a side channel vulnerability in its implementations. I'm going to show these 3 modifications first and explain how a new side channel vulnerability is introduced to with such changes. Okay, I'm starting with the receiving scheme. Let's look at this sequence number space first. In TCP header, sequence number is 32 bits long, so there are 4 billion different values. The blue area is called receive window, while the green area is out of window. Before RFC 5961, when sender sends a SYN packet, if the sequence number is out of window, receiver will send an ACK back. Otherwise, receiver will reset this connection immediately. An all-pass attacker might tear down TCP connection by injecting spoofed SYN packet. A valid SYN packet will cause receiver to believe that the sender has restarted. Since any value in window can reset this connection, attacker can brute force receive window instead of brute force each sequence number. To mitigate this attack, RFC enforces the receiver to send a challenge ACK to sender to confirm if it's indeed restarted. Now let's look at the reset receiving scheme. Before RFC 5961, it's similar compared to SYN receiving scheme. Connection will be reset when the sequence number is in window. To mitigate this attack, RFC requires the receiver to reset this connection only when the guest sequence number exactly match to receive .next, which is the next expected sequence number. For the rest in window sequence number, receiver will send a challenge ACK to confirm if sender indeed terminated this connection. Since our pass attacker cannot receive this challenge ACK, it needs to be extremely lucky to guess one number out of 4 billion to be able to succeed. Now let's look at data receiving scheme. When a packet arrives, the receiver first checks the sequence number to make sure it is in window. After that, the ACK number will be checked. Now let's look at the ACK number space. We call this blue area accept window here, while the red part is out of window. Before RFC 5961, ACK is valid as soon as it's located in accept window, which is effectively half of the space. Therefore, a blind outpass attacker do not have to guess the ACK number. Well, instead, after attacker finds the sequence number in receive window, it can simply guess twice. After RFC 5961, a new window called challenge window is introduced. This window is designed to minimize the accept window. Well, therefore, the probability that guess the ACK number hit in this window is minimized, while prevents dropping a legitimate response. In this way, after RFC 5961, when ACK number is in this challenge window, receiver will send a challenge ACK back. It doesn't change the rest cases. Well, in summary, RFC enforces a much stricter check on incoming packets to make our pass attack extremely hard. When 4 tuples are correct, challenge ACK will be triggered when it's a SYN packet with any sequence number, or reset packet with in-window sequence number, or data packet with in-window sequence number and old ACK number in challenge window. We can see the different type of packets need different level information to trigger challenge ACK. In our work, we utilize this feature to guess port number first, then we guess sequence number. With those values, we can further guess ACK number. How to use this challenge ACK to guess those values is done by using our discovered side channel. Well, this side channel vulnerability is introduced. Oh, sorry. Okay, this side channel vulnerability is introduced in Linux kernel by implementing a relimit or challenge ACK scheme in same RFC. This mechanism is designed to reduce the number of challenge ACK packets to save resources. And RFC marks it as should be implemented. Now I'm going to explain the vulnerability that we found. Well, we know that whenever we share states, it can potentially introduce a side channel, right? In Linux kernel 3.6, this challenge ACK scheme was first implemented. A global system variable was introduced to control maximum number of challenge ACKs per second. It is set to 100 by default. As this limit is shared across all connections, including the connection established with attacker. So this shared state can be exploited as a side channel. For example, attacker can simply establish a regular connection with server and send 100 reset packets with wrong sequence number to trigger maximum number of challenge ACK. If a challenge ACK, since challenge ACK is rarely triggered in regular traffic, it is likely for attacker to receive 100 challenge ACK. In this example, I also want to highlight that client can run any operating system since we only exploit the side channel at server. Now I'm going to show how this side channel vulnerability can be utilized by using guess and check method. At first, attacker sends a spoofed packet with a guess value. Then attacker can use its regular connection with server to check if this guess is correct or not. For example, if attacker wants to guess a correct client port, attacker can send a spoofed packet with client's IP address and a guess source port. At server side, this incoming packet will be considered as client's packet. If this source port is matched, Server will send one challenge ACK to client. After that, attacker uses its own regular connection to send 100 reset packets at the same 1 second to trigger maximum number of challenge ACKs from server. Since this challenge ACK rate limit is shared across all connections, if server has sent one challenge ACK to client, an attacker can only receive 99 challenge ACKs, like here. In this example, the blue arrow is a spoofed client packet, which is sent in guest phase, while the red arrow are packets in attacker's regular connection, which is sent in check phase. Well, guest and check phases, they have to be at the same 1 second. Similarly, if it's a wrong guess, no challenge ACK is sent to client, so attacker can receive 100 challenge ACK from server. This difference number of challenge ACK received by attacker can indicate whether he or she made a correct guess or not. But here we have one challenge. In guess then check method, the guess value can be confirmed only at the end of the second due to the way rate limit is implemented. So if we only test each value at each second, the time cost will be really expensive. Therefore, attacker can probe multiple values in 1 second, and he or she can know if a correct value is included in this range. Given this range, how to find specific value will be explained later. In our work, we define n as the maximum number of probing packets in 1 second. This value depends on the bandwidth of current network. Okay, similar to find port number, sequence number in window can be inferred by by sending such guess and check method with a reset packet with when 4 tuples are known. Attacker can indicate whether the sequence number is in window or not by checking the number of checked ACK received. Well, same process can be done to infer ACK number in window by sending a data packet when 4 tuples and sequence number are known. In summary, in traditional brute force attack, they are finding a correct packet with all possible combination, an open number, sequence number, and ACK number, which has 10 to the power of 22 different values. On the other hand, our attack can infer those values separately. This is a huge time cost improvement, since it changes time cost additive instead of multiplicative. This improvement makes it possible to finish our attack within 1 minute. Well, in our work, we have some more optimizations, including binary search to reduce the number of probing rounds, or multi-beam search to further reduce time cost. In addition, to handle packet loss problem, we add a redundancy encoded search. In this presentation, I will go over the binary search only. If more time left, I will further explain the other ones. Well, let's look at binary search for algorithm. The idea is to narrow down the search space by half at each round. Attacker can probe all packets in half range. If attacker receives less than 100 challenge ACK, then a correct value is included. If attacker can, attacker can use this half range as a new search space, and so on. Okay, now I'm going to show how to use a previous method to achieve our attack. I will give an attack overview first, then explain how each step works. Here is the attack overview. Given client and server, we already know source IP, destination IP, and destination port number. For example, to attack connection between client and USA Today website, attacker already knows their source IP is client's IP address, destination IP is server's IP address, and then destination port is 80. Therefore, attacker just needs to guess source port number to infer the existence of TCP connection. To further, like this, and to further get sequence number to do connection termination attack. In addition, attacker can guess all those values and ACK number to do hijacking attack. In the following slides, I'm going to explain each step. Let me describe time synchronization first. In general, the more packets are sent in guest phase, the faster our attack is. As mentioned before, the challenge accurate limit is on a per second basis. Guess phase and check phase should be at the same 1 second. Therefore, synchronizing time between attacker and server is very important, as more packets can be sent in the beginning of the 1 second interval. In our work, we propose a time synchronization strategy based on the side channel. The idea is to send 200 in-window reset packets spread out evenly in 1 second and check if we can see more than 100 challenge acts. In our strategy, we can finish time synchronization in 6 seconds. You can find more information in our work, in our paper, sorry. Well, let's look at inference of possible TCP connection. Given source IP, destination IP, and service at server, the main idea of this attack is to test if client open a source port. Therefore, attacker can use guess then check method to infer this port number. At first step, attacker probe n ports at each second to see if a client port is open throughout all ports number space. As soon as we find one range, we are safe to say that this connection is active. If attacker wants to guess exact port number in use, attacker can select correct range and use binary search or multi-beam search to find the exact port number. Well, TCP connection termination attack. As mentioned before, after RFC 5961, a reset packet works when it has the correct 4 tuples and exactly match sequence number. Since we have inferred source ports from last step, we just need to find the correct sequence number here. Well, different from port number, our side channel can only tell us whether sequence number is in window or not. This can be utilized as one optimization. Instead of probing each sequence number, we probe each sequence window by guessing only one sequence number in one window range. Here is a termination attack process. First, attacker divides their whole sequence number space into smaller range and probe one range in 1 second. Different from port number search, this range includes n windows instead of n values. Second, attacker selects their found range and use binary or multi-beam search to narrow down this range to a single window. In third step, attacker is finding the exact sequence number by locating the left boundary of the receive window. Attacker can use binary search or multi-beam search to find the sequence number. Since the attacker is using a spoofed reset packet to guess the sequence number, connection will be terminated automatically when a correct sequence number is guessed. Well, in order to hijack the connection, attacker has to know the correct 4 tuples, sequence number, and ACK number. Besides, the connection should be alive, so attacker can further inject data in it. Unfortunately, one cannot keep the connection alive if we use a reset-based sequence number inference. If we repeat reset-based sequence number probing, the reset packet will hit the correct sequence number to terminate this connection. Therefore, we break the 2 steps and reuse only the first step to infer rough sequence number. Then we take a detour to first locate the rough ACK number, which will allow us to find the exact sequence number later. Different from termination attack, hijacking attack use data packet-based probing instead of reset packet. Therefore, next sequence number can be found without resetting this connection. Now let's look at our evaluation part. I will first talk about time microanalysis, then I will show you case study of termination attacks and hijacking attack. Here is the time cost in our work. Let's look at figure 1 first, which shows the time cost by each step by using binary search or multi-beam search. This x-axis identifies different steps, while the y-axis indicates the time cost. We can see that the most time consuming part is sequence inference, which is caused by linear search to locate the receive window. Besides, it shows that multi-beam search saves about half time compared to binary search. Okay, now let's look at figure 2, which indicates the chance of time cost in total impacted by attack intensity. Obviously, the more packets we send per second, the faster the attack can finish. The red line shows the time cost variation. The large variation is caused by randomness of port number, sequence number, and ACK number. Furthermore, according to figure 2, the decrease rate tends to be smaller since attacker intensity is approaching the bandwidth limit, which leads to a higher packet loss rate. Therefore, if a higher bandwidth of network is provided, our attack can be achieved in a shorter time. For termination attack, we have 2 case studies, EC2 and Tuan network. In our Amazon EC2 experiments, attacker is located at UCR campus, while the victim server are different EC2 servers from different countries. For legitimate purpose, we attack our own connection for obvious reasons. In our experiments, we have tested 8 different regions around the world with a 96% average success rate and average 42-second time cost. Similarly, our second case study is Tuan network. Tuan network choose random relays to provide anonymity. In our work, we set our own client nodes as entrance relay, and it's connected to some random middle relay nodes all around the world. In our experiments, we terminate these connections with 89% success rate and average 61 seconds. With this attack, we believe that user privacy may be breached, since their Tor connection may be forced to route to some suspicious nodes or paths. Now let's look at hijacking attack case study. Our target is any long-lived TCP connection that does not use SSL or TLS, including news, website, and advertisement connection. In this case study, we picked a news website, USA Today website, which has a long-lived TCP connection that periodically refresh data every 30 seconds. This gives ample idle time for our sequence number and ACK number inference. Once the numbers are inferred, we perform a desynchronization attack, so the attacker no longer needs to worry about a race condition with server. This synchronization attack is done sending a spoofed request to server to increase the expected ACK number at server side. Although server will send a response to client automatically, this response won't be accepted since it contains invalid ACK number. Later, when the client initiates a real request, the server will no longer accept it since the sequence number is too old. In our work, after synchronization attack, the attacker simply sends spoofed response periodically every few seconds. The responses are crafted such that they are acknowledging requests that haven't been sent by clients yet. If such spoofed response arrive before the client sent a request, they will simply be ignored. As soon as the client does send out the next request, the spoofed response will become valid and accepted. The response can contain malicious JavaScript, and that allows phishing or even opportunities to exploit vulnerability in the browser and underlying operating system. In our experiment, we successfully hijacked the connection with an average 90% success rate. Besides, we injected a phishing window and client side with 80% success rate. This rate is lower than USA Today, since USA Today this rate is lower since the USA Today occasionally switch the HTTP request from one type to another. Therefore, the injected payload will not match the request all the time. In addition, the time of injecting a phishing window is 81 seconds. Regarding this serious vulnerability, we propose 2 possible defenses in our work. The first one is to add more random noise to this side channel to confuse the attacker. The second patch is to disable this global rate limit. This can be done by eliminating the global count in Linux kernel. In July 2016, Linux kernel patched this vulnerability by using first method. They also plan to use second method in the future. However, the newest Linux kernel haven't been applied to the in most Linux distributions. In order to patch the vulnerability temporarily, any administrator can disable rate limit in their own server. In conclusion, we discover a subtle yet critical flaw and implement in the design and implementations of TCP in Linux kernel 3.6 and beyond. We also demonstrate possible blend of path attacker with about 1 minute. Sorry. At last, we propose defense schemes. That's all. Thank you. Any questions?
Time for some questions.
Your talk is about the Linux kernel.
Yeah.
Have you found this anywhere else, such as perhaps in BSD kernels implemented similarly, such as in Zhiyun OS, such as you could attack BGP sessions?
Yeah, in our experiments, we also tested Windows, Mac OS, and also the Federal, I think. Yeah, for those Linux, for the other OS operation systems, we haven't found these vulnerabilities because they didn't implement RFC 5961 completely.
Hi, Roger Dingeldine from the Tor project. Hi. Great stuff. I wanted to follow up a little bit about the Tor attack you were describing. You were speculating that if you can break connections inside the Tor network between relays, then you can drive circuits, you can drive clients to build circuits the way you want.
Yeah.
When a connection inside the Tor network fails, the client chooses an entire new path without any memory of what failed or succeeded in the past.
Yeah.
So you basically have to break all of the connections and keep them broken until the client chooses exactly the very low probability path that you want. So I don't think that attack would work, but I think we should really keep thinking about how to use this sort of attack to undermine anonymity or, or attack overlay networks like that.
Yeah, good question. I totally agree. Well, but this DOS attack will be extremely hard for Tor network to breach its privacy. But in our experiments, we also found for Tor networks, they have a website listing all possible relay nodes. So we can brute force all those relay nodes and trying to reset all connections starting or ending to these relay nodes. This is one possible solution, but it's still very hard and takes a lot of time. Okay.
Okay, so I have one. So
okay.
I know you guys have done quite a few work in this space, right? What's your next one?
Well, it's very exciting to find these vulnerabilities in Linux kernel. And one possible way we are thinking is that we can, a simple way to measurement how widely this vulnerability existed in the Linux systems. For example, even those vulnerability is patched, some servers, they are still using an old version of Linux kernel. So it's still a very serious problems around the world. And besides that, it's also very interesting for us to think whether or not we can find a similar side channel in Linux kernel about by utilizing some other mechanisms.
Okay. Looking forward to that. Any other question? Okay, thanks Biko one more time.
Thank you.